Well, in this report, I will be explaining the steps involved in the configuration of the Quartus software to program the Max-10 FPGA. So I'm going to be explaining the code of the logic gates and how it works and what are the inputs and outputs of the code itself. Now, I'm going to be explaining the first one, that is the VHT. So the VHT code defines an entity named logic gates representing a model for various logic gates. The entity comprises two input ports, which are X and Y, and seven output ports that are the logic gates: the AND, NAND, OR, NOR, XOR, XNOR, and SNOT, each corresponding to a different logic gate operation. Within the architecture section behavioral, the behavior of the logic gates model is specified. Consecutive signals assignment determine the output signals based on the input signals X and Y. Now, S AND represents the logic AND operation between the input signal X and Y. S NAND represents the logic NAND operation between the input signal S and Y. S OR represents the logic OR operation between the input signal X and Y. S NOR represents the logic NOR operation between the input signal X and Y. S XOR represents the logic XOR operation between the input signal X and Y. XNOR represents the logic XNOR operation between the input signal X and Y. And S not X represents the logic NOT operation applied to the input signal Y. These assignments define the output of the logic gates model based on the inputs X and Y, demonstrating the behavior of the different logic gates such as AND, NAND, OR, NOR, XOR, XNOR, and NOT, like so. Now I'm going to be explaining the logic gates VHT. Well, in this case I'm going to be explaining the part of the code that says begin. Well, in this part of the VHT code represents a sequence of signal assignments and delay statements that execute only once. Here's a breakdown of what each line does. In the first line, the value zeros to the signal X. In the second line, the value 0 to the signal Y. Then it will wait for 10 nanoseconds. After the delay, the same process repeats from different combinations of the signal values. In this case, 0 is assigned to the X and 1 to the Y. Then it will wait for 10 nanoseconds. Then 1 it will be the value of the X, and 0 it will be the value of the Y. And then it will wait another 10 nanoseconds. Finally, 1 is going to be the value of X and 1 is going to be the value of Y, and then it will wait for 10 nanoseconds. This sequence of assignments and delays is useful for initializing or testing digital circuits, as it provides a controlled sequence of input signal combinations followed by a delay to observe the circuit's behavior. Once you have these two codes, the VHT and VHT, you can continue the process of the configuration of the FPGA of the Max-10 of Intel to program your logic gates in the FPGA. So you will need to assign the pins and the outputs of your FPGA, and doing so you will be uh, watching how the FPGA works in physical.
Hi everyone, I'm gonna be explaining how the logic gates works in a FPGA university program from Intel. Now, these two switches are X and Y, and these LEDs are the logic gates and that are the outputs of this FPGA. Now, I'm gonna be explaining the first case, and this case is the AND, and this works when both inputs are in 1 and the LED will be on in the output. In any other case, it will be 0, as you can see. Now, I'm going to be explaining the NAND. This has 4 cases, and it will be in any case that is 0 and 1, it will be equal to 1 in the output. 1 and 0 will be 1 in the output, and 1 and 1 will be 0 on the output. It's the opposite of the AND, sorry. Now I'm gonna be explaining the NOR. The NOR, it says 1 in the switch X and 1 in the switch Y, it will be equal to 0 on the output NOR, as you can see in this LED. Now, in 1 in the switch X and 0 on the switch Y, it will be equal to 0 on the output NOR. Now, 0 in the switch X and 1 in the switch Y will be equal to 0 on the output NOR. And the last case, it will be 0 in the switch case X and 0 in the switch Y. It will be equal to 1 in the output NOR. As you can see, it's on the LED number 3. Now I'm going to be explaining the OR. 1 in the switch X and 1 in the switch Y, it will be equal to 1 in the output OR, as you can see. Now, 1 in the switch X, 0 on the switch Y, it will be equal to 1 on the output OR, as you can see. Now, 0 on the switch X and 1 in the switch Y, it will be equal to 1 on the output OR. Now, 0 on the switch X, 0 on the switch Y, it will be equal to 0 on the output OR. Now I'm gonna be explaining the XNOR. The XNOR, 1 in the switch X, 1 in the switch Y is equal to 1 on the output XNOR. 1 in the switch X, 0 on the switch Y will be equal to 0 on the output XNOR. Now 0 on the switch X, 1 in the switch Y will be equal to 0 on the output XNOR. And the last case, it will be 0 on the switch X, 0 on the switch Y will be equal to 1 on the output XNOR. Now, the XOR. 1 on the switch X, 1 on the switch Y will be equal to 0 on the output XOR. 1 on the switch X, 0 on the switch Y will be equal to 1 on the output XOR. 0 on the switch X, 1 on the switch Y will be equal to 1 on the output XOR. And now 0 on the switch X, 0 on the switch Y will be equal to 0 on the output XOR. And finally, the NOT. The NOT is the LED number 4. 1, 2, 3, 4. And this is the negate of the Y in my case. And if it's off, it will be the LED on. And if it's on, the switch, the LED will be off.